Hello, let's talk about a binary search, a commonly used algorithm during programming competitions or algorithmic interviews. So background is like it's used essentially search for root of a monotonous function. So time complexity is often log n for discrete cases, if we have some array of size n and trying to find something in it, or of log c for real numbers cases with numbers values up to c. Maybe you can also divide by epsilon, where epsilon is precision you need to achieve. Suppose we have some f from x equals to 0 equation. It can find L and R such as if L is less or equal to 0 and if R is more than 0. So the root is in the interval from L inclusive to R not inclusive. We can actually just check for if it's like equal to 0 for L. We just return early. Then we can take some approach from m equals to L plus R divided by 2 and check if m, if it's less or equal than 0, then the root is in interval mr, otherwise it's in Lm. So in both cases we've reduced the interval length by roughly 2x. In discrete cases it would be like approximate, like in real number cases it would be like pretty much equal to 2x decrease. And this means that eventually we get, like for discrete cases, we get r equals L plus 1, and then L is the root, or like some FL, or like element at position L is the root, or basically the number we are looking for. And for real number cases, we just get to like r minus L less than some epsilon, where it's precision that we need, then L is the root with a precision epsilon. And yeah, that's where we get logarithm, because every time we like exponentially change the length of the interval. So number of steps would be like logarithmic. Let's take a look at an example. Like a classical problem would be find an element in a sorted array. Have some number k, and we may need to find if it appears or not in a short amount of time. You can also find variations when, for example, find the biggest element which is less or equal than k. So first we check for each cases a0 more than k, or like an minus 1 less than k, or an minus 1 equal to k for an early return. Otherwise we can set L equals to 0 and R equals to n minus 1. So AL is less or equal k and AR is more than k in this case. And we can apply binary search until an element cell becomes 1, or like we can early return if AM is equal to k. Suppose A is equals to 1, 3, 4, 6, 9, and k is equals to 6, so the number would be present. We start with L0, R4, M becomes equal to 2. AM is less or equal than k, so we assign L to M. Then we go with 2, 4, M is equals to 3. AM is actually equal to k, so we can return early. In discrete cases, you like depends on the case. If you're like looking for something precise, you can return early. In real number cases or some discrete cases, when you're looking for something like maybe not exact, you can sometimes keep going until you end with like r minus L equal to 1. And in this case, if the number wouldn't be present, in the end, when r minus L is equals to 1, you just check, hey, what's AL is equal to? Is it like k or not? So another one is find the longest repeated substring. Given a string s of length n, find the longest consecutive substring which appears in s at least twice. So we can take a look that we can do, of course, brute forcing, but it's going to be very slow. But we can know that length of substring research is based on monotonous function, since if we have a substring of length k, which is repeats at least twice, then we also have substring of length k minus 1, which also repeats at least twice. Because we can just like remove one character and it's also still use like same occurrences. So we can apply binary search on the length of the substring with L equals to 0 and R equals to n. We can also use hashing when we like traverse for a fixed length to filter out unequal substrings more efficiently. So for example, if S is like A, B, C, D, A, B, C, so we start with 0 and 7, M is equals to 3. There is a suitable substring ABC of length 3, so we assign L to M, and then like we have two steps where we just basically move R because well, 3 is actually the answer for this problem, so we end up with like L equals to 3, R equals to 4, exit condition satisfied, so the result is L equals to 3. If we need to return the string itself, we can also save it when we like compute the lengths. We also like save what's the actual current candidate. Cool. So some homework would be solve an equation in real numbers x cubed plus 2x plus 1 equals to 0 with a precision at least 10 power minus 6. Another problem is given an array A of positive integer of length n and the integer k. Find the longest consecutive subsequence where the sum of the numbers is less or equal than k. Like for example, for like 1, 3, 1, 1, 2 and k equals to 4, we have an answer 3 due to like just subarray 1, 1, 2. And actually, like this problem can be solved without binary search. So try like we can try a variation of actually never mind. Yeah, another problem is like given a string s of length n, find the longest consecutive substring where its reverse also appears in s. So for s equals to ABC, ABC, BA, the answer is ABC because we have ABC and CBA. Okay, so pause for now. I'm gonna be doing analysis of these problems as well shortly, but try to do them independently first. Okay, so now let's do analysis of the problems. So first one, like you can try to check some like maybe like by -1, it gives you like the left side is less than 0. If you check like 0, it's already more than 0. So the root, like there may be some roots like between 0 and like -1 and 0. But also like it's cubic equation, so there is no like simple formula for finding this. So there is a formula, but like it's easier to find it programmatically using binary search. Why can we use a binary search? So when we compute the derivative, it's going to be 3x squared plus 2. So it's always positive, so the function is monotonously increasing. So in this case, we can just start with L equals -1, R equals to 0, and do binary search until like R minus L becomes like less than 10 in power -6. That's going to give us the answer. So for the second problem, we can do a binary search for the lengths of this subsequence, and then like on every step we just like compute the sum, and then we like add element, remove element, add element, remove element. So when I talked about that this can be solved without binary search, you can actually just do a while loop and like just use methods of 2 pointers because it's positive integers. With negative, if negative integers are appearing, then it gets a bit trickier, then there may be like more edge cases, and then the algorithm may become like more complex. You don't no longer have like easy like monotonity. And then for the last problem, it's similar for a repeated substring. Again, like we have the same property that if we have a substring which has like in reverse for length k, we also have the answer for k-1, k-2, etc. So what we do, we do binary search for this like lengths, and then we compute all the hashes and put like indexes of strings for direct for like from left to right, and then like we do then loop from right to left. Also compute the hashes and check if the hash is present. We just check, hey, is it equal to any of the strings? And expected time would be like pretty small. Basically, we get like n log n complexity. because if we get a good enough hash function, then like if strings are not super long, then like we would have only very few collisions, and most likely if we have a collision, then like we gonna actually have a match. But we still need to check because it's not guaranteed, and the birthday paradox as well. Cool, thank you for watching. Let me know if you have any questions.